Okay, problem 2. So, on problem 2, we are going to follow Han and Leia and Chewbacca and everyone to 2 different places where they seem to have the same surface gravity as Earth. And we want to find the relationship of the densities of these places to the density of Earth. So, we start with, so let's just, in general, say, let's recall from the previous problem that little g on the surface is going to be big G times the mass of whatever you're standing on divided by the square of the radius of whatever you're standing on. Okay? And so this is the same for Earth and for the asteroid and for Bespin. So G for the Earth equals G for the asteroid equals G for Bespin equals whatever. Okay, so let's see where we can go with this. We want to find the density, the ratio of the densities of these things. So density of, I'm going to say density of the asteroid, since that's the first one, and it begins with A, over density of Earth. Okay, so density, as you'll recall, is mass divided by volume. So that's going to be the mass of the asteroid divided by 4/3 pi times the radius of the asteroid cubed, okay, over, and then the density of the Earth is, of course, the same thing, but for Earth. And what you will notice, of course, is that you can very easily cancel the 4 pi's now, or the 4/3 pi's. Now remember that this stuff here is all underneath the MA, right? So this, for example, down here, this volume of the Earth is in the denominator of the denominator. So what that means really is denominator of denominator is numerator, of course. So mass of the asteroid times r radius of Earth cubed over mass of Earth times radius of the asteroid cubed. And then you can say, let's see, where are we going from here? Okay, so then what we need to do, we're given the radius of the asteroid, and we know the radius of Earth. We are not given the mass of the asteroid. So what we have to do is find the mass of the asteroid from the fact that the asteroid seems to have the same surface gravity as Earth. So remember that G for Earth equals G for the asteroid. And so I'm going to expand on the left side, I'm going to expand G for the Earth is big G times mass of the Earth over radius of the Earth squared. And for the asteroid, big G times mass of the asteroid over radius of the asteroid squared. And so what we can do now is, let's see, we can cancel, come on, there we go, cancel the big G's, of course. And then we can say that, right, okay, so then we can say that what we had was, yeah, okay, so what I want to do is solve for MA over ME, because what I have in here, you see this MA over ME, so I want to take this equation up here and solve it for MA over ME. So I'm going to divide the ME through to this side and get MA over ME equals, and I'm going backwards here just to keep things on the same side, RA squared over RE squared. Okay, so now, using that result, we can say that we can take this thing here, and substitute in this expression. So we can say rho A over rho E equals MA over ME is RA squared over RE squared. And then we also had over here RE cubed over RA cubed. And that, so when you do all the cancellation, that just equals RE over RA. So this is really our answer here, is that density of the asteroid over density of Earth is equal to radius of Earth divided by the radius of the asteroid. Whoops. Well, why? Where's my, oh, there we go. Okay. Radius of the asteroid. And so as I recall, the asteroid has a radius of 500 kilometers, and the Earth has a radius of 6,371 kilometers. So that means that the asteroid, 12 points, that's right. So rho A, density of the asteroid over density of Earth, is 12.7. And that makes the asteroid very dense. I think it's probably denser than any, I mean, it's got to be made of all metal. It's got to be really freaking dense in order to be correct, okay? then meanwhile, I mean, we can do the same thing for Bespin, right? And we just say density of Bespin over density of Earth is equal to radius of Earth over the radius of Bespin. And as it happens then, density of Bespin over density of Earth is equal to, since Bespin is conveniently, what did I say, it's 100 times the radius of the asteroid, so conveniently then the answer there is 0.127. And as I recall, that actually puts Bespin's density about on par with Saturn. So, and the radius of Bespin is slightly less than Saturn. So Bespin actually is realistic. I mean, for a gas giant, right, if you're going to float in the top of the gas giant, it's much bigger, it's much more massive, but it's so much less dense that you're further away from the center. And you could actually, obviously you can't stand on the gas, but if you had the floating city in the upper regions of the atmosphere, then you could in fact have, you know, a reasonably tolerable level of gravity inside the little city. So that actually is realistic if there's just, as long as there's some way to keep the city up, big balloons or whatever. The asteroid, you know, I don't know. I don't know if there is anything quite that dense. Anyway, so there's your answer.